You're staring at something that looks like it should dissolve. Pale, translucent, soft as wet tissue paper, and it's alive 8 kilometers below the surface of the Pacific Ocean. September 2023. The Izu-Ogasawara Trench south of Japan. A deep-sea lander carrying cameras and bait had been sinking for hours through cold and absolute dark. The crew on the research vessel above felt nothing. The fish below felt everything. When the lander's lights hit the seafloor at 8,336 meters, a small creature drifted into frame, unhurried, pale pink-white, its organs faintly visible through its own skin. It moved like a piece of wet paper bending in a slow current. This was a snailfish. It had just broken a record no one expected to be broken. Alan Jamieson, chief scientist at the University of Western Australia's Minderoo UWA Deep Sea Research Centre, led the expedition alongside Thomas Linley of Newcastle University. Jamieson later said, "We have spent over 15 years researching these deep snailfish. There is so much more to them than simply the depth, but the maximum depth they can survive is truly astonishing." The previous record was 7,703 meters, filmed by a Jamstec team in the Japan Trench in April 2008. This new footage added 633 meters. In deep-sea terms, that is not a small step. That is a different world. Here is the problem. At 8,336 meters, hydrostatic pressure reaches 830 atmospheres. That pressure would collapse a human skull in milliseconds, steel bends, titanium warps. And this fish, no rigid skeleton, no hard scales, no armor of any kind, was navigating it casually. The biology makes no sense on the surface. The creature appeared structurally wrong for the environment, fragile where everything should be reinforced, soft where everything should be rigid. But here is what the footage could not show. What was happening inside that tissue at the molecular level? Something was keeping those proteins folded. Something was holding the chemistry together. By the end of this video, a specific molecule, one your own body produces in small amounts, will explain exactly why this fish exists at all. And science has already calculated the hard number, beyond which even that molecule fails. The obvious explanation writes itself. Deep-sea creatures survive pressure because they are built tough, reinforced, armored, dense. Like a submarine, thick steel walls engineered to resist compression from every direction. That logic is clean. It is also wrong. The snailfish has no scales. Run a finger along its body, and you would feel smooth, translucent membrane tissue so soft, it deforms under its own weight when lifted from water. There is no armor. No rigida outer shell. Nothing between that creature and 800 atmospheres of pressure, but a thin layer of mucus-rich skin. The skeleton offers no more reassurance. Surface fish carry dense, mineralized bones, structural architecture designed to hold shape. The snailfish skeleton is partially cartilaginous, reduced, almost vestigial. Mackenzie Geringer at the State University of New York described it as barely more than scaffolding. Then there is the swim bladder. Most fish use one, a gas-filled internal cavity that controls buoyancy. At Haddle depth, a gas-filled cavity would collapse instantly. So the snailfish simply never evolved one. The organ is absent entirely. Every structural feature we associate with surviving extreme conditions is missing, not reduced, missing. Density, rigidity, reinforcement gone. By the submarine logic, this animal should not exist. The pressure alone should crush soft tissue, denature proteins, halt cellular function. 8 kilometers down, water exerts 830 times the pressure at the surface. Hadal snailfish are extremely well adapted to living in the deepest places in the ocean, Geringer told National Geographic in 2017. But adapted how? That sentence describes the outcome, not the mechanism. The structure of the animal explains nothing. Every measurable physical property points toward catastrophic failure at depth, and yet the 2023 footage from the Izu-Ogasawara Trench shows one moving, feeding, alive. So, if the body offers no mechanical resistance, If toughness is not the answer, then something else is keeping those proteins intact, something chemical, and that answer runs deeper than the skeleton ever could. The story pivots here on a molecule, not a skeleton. Paul Yancey, a biochemist at Whitman College, spent years analyzing tissue samples from deep-sea fish. In 2014, publishing in the Journal of Experimental Biology, he identified something accumulating inside Hadal snailfish at concentrations unlike anything seen in shallow water species. A molecule called trimethylamine N-oxide, TMAO. At the surface, TMAO exists in fish tissue at low levels, unremarkable. But in Hadal specimens collected from below 6,000 meters, Yancey found concentrations climbing in direct proportion to depth. The deeper the fish, the more TMAO packed into every cell. The reason matters. At extreme pressure, proteins denature. They unfold. They stop working. TMAO physically counteracts that process, stabilizing the protein's folded shape at the molecular level, keeping enzymes functional where chemistry alone would fail. Mackenzie Geringer at the State University of New York at Geneseo confirmed this in 2017, examining snailfish biochemistry directly. The TMAO wasn't incidental, it was structural. A chemical scaffold replacing the physical armor the fish never had. Not bone, not scale, a molecule. So the pale, translucent body, filmed at 8,336 meters in September 2023, wasn't surviving despite looking fragile. It was surviving because of what was dissolved inside it, at concentrations that would be toxic to any fish living in sunlit water. But Yancey's data contained something else, something the 2023 expedition would eventually force into sharp focus. TMAO concentration has a ceiling. The molecule accumulates with depth. Yes, but biological tissue can only hold so much before the chemistry inverts, before the solution becomes the problem. Yancey's models pointed to a hard biochemical limit somewhere just beyond 8,000 meters. The 2023 specimen was filmed at 8,336. So how close was it to that ceiling, and what happens to any fish that crosses it? Here is the problem nobody wanted to find. TMAO works. The chemistry is real. The deeper the fish, the more TMAO accumulates in its tissue, and the more stable its proteins remain under crushing pressure. That logic held for every depth sampled before 2023, clean, consistent, elegant. But Paul Yancey kept running the numbers forward. If TMAO concentration scales with depth, there is a point where it stops helping. Yancey and Siebenaler published the modeling in Frontiers in Marine Science in 2023. At concentrations above 400 millimoles per kilogram of tissue, TMAO does not stabilize cells, it destabilizes them. The molecule that saves the fish becomes the molecule that kills it. That ceiling, calculated purely from biochemistry, sits somewhere between 8,200 and 8,400 meters. The 2023 snailfish was filmed at 8,336 meters. That number lands differently now. Not a record, a proximity reading. The animal was filmed within 64 meters of the theoretical outer edge of what carbon-based biology can chemically sustain. Not comfortably inside the window, at the far wall of it. A researcher at Whitman College, working from tissue concentration data, had drawn a line across a whiteboard. The snailfish was on the wrong side of comfortable. The story was never about how deep the fish went. It was about how close the fish was to the last possible depth any fish can ever reach. Not a record to be broken, a ceiling, hard, chemical, absolute. Below 8,400 meters, the math runs out for vertebrate life entirely. No amount of evolutionary pressure can push TMAO past its own toxicity threshold. The ocean goes deeper, life cannot follow. So if the 2023 snailfish was already near the biochemical limit, what does the tissue actually look like at that concentration? And what did the 2023 samples reveal? Here is what the video promised: a specific molecule, One your body also makes, in trace amounts, and a hard number science has already written down. The molecule is trimethylamine N-oxide, TMAO. Paul Yancey at Whitman College identified its role in deep-sea fish tissue more than a decade ago. At the molecular level, it physically counteracts hydrostatic pressure. It keeps proteins folded, functional, intact. Without it, pressure at Hadal depths would denature proteins the way heat denatures an egg. The chemistry stops working, and the animal stops being alive. Here is what makes the 2023 footage different from every prior record. The snailfish filmed at 8,336 meters in the Izu-Ogasawara Trench by Alan Jameson and Thomas Linley's team aboard the Minderoo UWA Deep Sea Research Center expedition was not just surviving. It was operating near the theoretical biochemical ceiling for TMAO accumulation. There is a ceiling because TMAO has a paradox. At surface concentrations, it is a stabilizing agent. At extreme concentrations, it becomes toxic. The deeper the fish, the more it accumulates. And somewhere between 8,200 and 8,400 meters, the math runs out. Beyond 8,500 meters, no known biochemical adjustment can compensate. The pressure wins. Carbon-based life, as currently understood, cannot chemically sustain it. That translucent animal, pale, soft, no rigid skeleton, no scales, no swim bladder, was not fragile. Every missing structure was a precise subtraction, less mass for pressure to crush, more room for chemistry to work. The thing that looked wrong was the answer. Mackenzie Geringer's 2017 tissue analysis at SUNY Geneseo confirmed the TMAO gradient holds across species and depth. The deeper the specimen, the higher the concentration, linear, predictable, bounded. The index concludes this. The snailfish at 8,336 meters was not an accident of survival. It was a carbon-based organism operating at the absolute chemical limit of what life on this planet can sustain, and we have the number.